Hi, I'm Etienne from Karlsruhe Institute of Technology in Germany. In this presentation, we would like to give you our investigations into uncertainty-driven exploration strategies based on offline to online reinforcement learning in the real-world robot bean picking scenario. This work is done during my master's study in the University of Stuttgart in collaboration with Bosch Center for Artificial Intelligence in Germany. So the existing grasp prediction approaches based on artificial neural networks in industrial applications are mostly based on offline or supervised learning, while ignoring the exploratory online adaptation to new scenarios, such as unseen objects with various textures, materials, and physical properties. To this end, we propose to construct our online learning system where both grasp reward predictions and grasp poses can be adapted into new scenarios with high efficiency. Specifically, we investigated various uncertainty estimation and calibration schemes that serve as the closed-loop online exploration based on Bayesian uncertainty quantification and distributional ensemble method. We first investigated our vision-based deep reinforcement learning baseline, namely CONSEC, which is a convolutional soft actor critic network specialized for real-world bean picking with a small-scaled pre-collected dataset as well. After that, we train our network continuously through limited iterations of real-world interactions with novel objects while ensuring their generalization ability to them. Inspired by recent success in multi-agent deep reinforcement learning, we investigated the probabilistic critic network of CONSEC, including Bayesian uncertainty estimation and quantile regression, which are successfully embedded in the CONSEC architecture and integrated into the exploration strategy through the Gaussian UCB approach. Our experiments demonstrate the efficiency of uncertainty-driven exploration and further verify the superiority of epistemic uncertainty over the aleatoric uncertainty as was proven in previous works. In addition, as inspired by APEX, we built a multi-process training schedule for efficient online learning from our uncertainty-driven framework as well. When discussing uncertainty in deep learning, we can often decompose it into two sources, namely the aleatoric and epistemic one. As an irreducible inherent noise, aleatoric uncertainty stems from the stochasticity of the environment that the agents are trained in within their learned knowledge, which reflects noise under observation, actions, and rewards during the Markov decision process. On the other hand, the challenge of effective exploration is connected to the epistemic uncertainty. This type of uncertainty represents the ignorance of the agents against the out-of-scope experiences, which may serve as a valuable guidance signal, or the intrinsic motivation for the exploration as was discussed and studied by preliminary works. Our value-based uncertainty estimation relies on the following two paradigms. The first approach models the final Q estimates as Gaussian likelihood, and another one stems from distributional reinforcement learning by applying Q ensemble in both methods. The aleatoric epistemic uncertainty can then be well modeled and disentangled. Here we modify the critic network through the integration of uncertainty estimation as mentioned above. Fed by RGBD images, we observe the concentration of aleatoric high uncertain area on the boundary of objects, while the epistemic one shows few highlights over the whole Q map in the source domain scenarios after offline training of each probabilistic COMSEC. We built a multi-process training schedule for efficient learning inspired by APEX. Each group of agents from the whole ensemble are updated in individual training processes. In the inference process, the data collection is served by the real-world robot bean picking. The exploration is executed through heuristic search over the whole UCB map, which equals the summation of Q map and discounted uncertainty map. Throughout the whole experiments, we apply the 6-soft robot with stereo camera for data collection, exploration, and performance evaluation. The objects that serve the offline data collection involves regular and opaque items, while the online objects are characterized by complex structures and even transparent surfaces, for instance. We aim to evaluate the generalization ability and efficiency of our strategy by analyzing the grasp success rate. Our experimental results shows that the exploration based on academic uncertainty gives the highest final clearing rate of above 90% with a relatively high grasp success rate as well, which is particularly effective in guiding the agent's exploration towards promising action, leading to more efficient and targeted experiences, resulting in faster and more effective learning. On the other hand, exploration using aleatoric uncertainty or total uncertainty may misguide the learning process, hence converge to a poorer policies and the baselines. To gain a deeper understanding, here shows the evolution of reward maps and uncertainty maps during the training process. Our observation shows that high reward regions tend to concentrate on the area of object that can be grasped safely, such as the center region of homogeneous surface. On the other hand, false positives on hard objects are the main exploration targets during the online learning. Exploring these areas can help the agent learn more effective strategies in the presence of uncertainty, such as transparent objects. In this way, agents may improve an understanding of the environment and reduce the number of false negatives. In a word, we are convinced that the uncertainty-based explorations generalize better to new objects and collect valuable online transitions in the long run. In the future works, we have following expectations. First, a more efficient, faithful, and domain-agnostic uncertainty estimation instead of naive bootstrapping with ensemble is highly expected. Second, since as proven in previous work, the uncertainty estimates can also serve as a guidance signal in consolidation-based continual learning. A scalable lifelong generalization of such a learning system can be pursued where the agents may retain the domain knowledge over the preceding experiences in the long run. In addition, a more efficient memory replay can also be beneficial for this closed-loop generalization. Thank you very much for your attention.